This here is the second part of Green's theorem. So we did the first part of Green's theorem, the circulation form. This is Green's theorem, the flux form. So we're talking now about outward flux of this vector field. So instead of rotation, we deal with outward flux. So it's got three parts just like the other one did, except instead of setting it up in terms of rotation, it sets it up in terms of outward flux. You'll notice that there's a part here where we talk about f dy g dx, but then we also write it in terms of a double integral of the partial f with respect to x, partial g with respect to y, this time with a plus sign in between them, again, integrated over the area. So sometimes if you can find the area of that base, find these values over here, multiply them together, it's a whole lot easier than turning everything into parametric form. All right, source-free vectors, a two-dimensional divergence is the sum of the partial f with respect to y, with respect to x, partial g with respect to y. If the divergence throughout the region is 0, we say the vector field is source-free. Right? If the divergence is positive, then the vector field acts as a source, right? Pushes out. If the divergence is negative, the outward force is negative, and the vector field acts as a sink. Not like somewhere where you wash the dishes, but like it pulls it in towards you. So if it has a two-dimensional divergence of 0, then we say that it's source-free. All right, so let's take a look at this example over here. I've got a vector field of y negative 3x over a region bounded by y equals 4 minus x squared. If I want to find the flux using Green's theorem, this is my f, that's my g. So the partial f with respect to x is 0. The partial g with respect to y is 0. And so if I add those together, I just get 0. Now, I could also check by taking the double integral of fx plus gy, so of 0 integrated with respect to the area, which it doesn't matter what the area is still going to give me 0. So yeah, the two-dimensional divergence, 0, so the vector field is source-free. Are they all that easy? Yeah, let's try another one. And then we'll try sort of an application that deals with integration of this, and then we'll be done. All right, so here's this vector field, x squared plus y squared comma 0 over the region bounded by the interior of the unit circle. So if I go to find my partials, the partial f with respect to x is going to give me 2x, right? That's this first piece here, f. That second piece is g, so the partial g with respect to y is 0. So if I add them together, that gives me 2x plus 0, which is 2x, so it's not source-free. If I want to find the flux, though, is it possible that the outward flux is 0? Now let's find out. In parametric form, x squared plus y squared is less than or equal to 1. We let x equal the cosine of t and y equal the sine of t. Then we can set this up. The derivative of cosine is negative sine. The derivative of sine is cosine, and these values work for t values from 0 to 2 pi. So the setup goes like this. The integral of f dy minus g dx. So f is going to be what? F is the first piece of our vector field, the x squared plus y squared. So the x squared plus y squared is going to give us cosine squared t plus sine squared t. So that's x squared plus y squared dy, which is cosine t, minus the integral from 0 to 2 pi of x squared plus y squared. Well, that's the first term. The second term is just 0 times the sine of t. So the f was the x squared plus y squared, the g was the 0. And then, of course, that takes care of that whole piece over here. This thing then just gives us the integral of cosine of t, because this piece here just goes to 1, 0 to 2 pi, and that'll give us sine of t at 2 pi and at 0, which is 0. So the outward flux then is 0. All right, where does Green's theorem really come in handy? suppose you had this integral over here, integrating over a closed curve of this thing. We've got two options. We can use Green's theorem, or we could set up parameters based on a unit circle. Let's try with the parameters of the unit circle first, and then see if Green's theorem offers us any shorter version of this problem. All right, so the unit circle can be set up with parameters as x equals cosine of t, y equals sine of t, which means that the dx, the derivative of cosine, would give me negative sine. The derivative of sine will give me cosine. All right, and so now I got to replace all of my x's, y's, and dy's and dx's with those four things that I set up. So the substitutions we need to make are based on this. 2x minus 3y dy minus 3x plus 4y dx. All right, so the x we said was cosine t, so we get 2 cosine t minus 3 sine t, and then our dy was a cosine t minus 3 cosine t plus 4 sine t, and then our dx is a negative sine t. All right, so this gives us a 2 cosine squared t minus 3 sine t cosine t minus 3 cosine t times a negative sine t, so that gives me a plus, minus 4 sine squared t. Oh, but wait, there was a negative out there, so now that becomes a plus. Okay. So these two things go away, and I can write this as 2 cosine squared t plus 2 sine squared t plus 2 sine squared t. So I'm taking this 4 sine squared t and splitting it up only because I know if I combine those two things together, I'll get a 2. And so now this gives me the integral from 0 to 2 pi of 2 plus 2 sine squared t dt. And now when I go to integrate that, well, I'm going to have to do something with that 2 sine squared. Well, let's turn the sine squared into a 1 minus cosine 2t over 2. And now those 2's will cancel. I haven't integrated yet. So I got to integrate 2 plus 1 minus cosine of 2t, which is the integral from 0 to 2 pi of 3 minus cosine of 2t. So that'll give me 3t minus sine of 2t over 2. Now evaluated at 2 pi and at 0. That gives me 3 times 2 pi. The sine of 4 pi over 2 is just 0. And when I put zeros in, I just get 0. So I get 6 pi. All right, that's using the parameter version of it. Is it easier to use Green's theorem here? Do you notice how nicely this thing is set up for Green's theorem? In that the first piece here, that's my f, that's my g. So the partial derivative of f with respect to x is just 2. And the partial derivative of g with respect to y is 4. Now, go back to Green's theorem. Green's theorem flux form says I can take the partial f with respect to x plus the partial g with respect to y and integrate it over the area. So let's do that. Let's take, here, I'm going to do it next to it for comparison's sake. let's take the partial f with respect to x plus g with respect to y, double integrated over the area. Well, this we said was 2. That we said was 4. What's the area? This thing here would be the area of a circle. Pi r squared. And we said the radius of the unit circle is 1, so the area is just pi. So I'm claiming that that's the equivalent of taking 2 plus 4 times pi. 2 plus 4 is 6. My answer is 6 pi. So look, without even realizing what I did Green's theorem in green. I'll let you compare the two of these. Is Green's theorem a time saver when you're integrating integral problems that are specifically set up in such a nice way? Yeah, very much so. Partial derivative of f with respect to x, partial derivative of g with respect to y, figure out the area of the base, add them and multiply, and you're done, and you save yourself all the parametric work that I have on the right-hand side. That's the end of part 2 Green's theorem.